Hi everybody, I'm Razvi. Welcome back to PWN101 series. In this video, we are going to solve the 8th binary from the PWN101 TryHackMe room. In order to do so, we are going to see and understand how we can abuse a format string vulnerability so as to write arbitrary values into memory. This time, instead of just leaking memory contents, we are actually overwriting it. Specifically, we are going to see how we can abuse the n format specifier from the printf family of functions in order to overwrite GOT or GOT entries. So let us get right into it. It is a 64-bit executable that determines the size of the registers and the addressing or wording of the CPU, which in this case both are 8 bytes long, and it also defines the calling convention this binary will use. Remember, in 64-bit executables, the 6 first parameters of the functions are passed via registers and the rest of them via the stack. We can also see there are canaries present on the stack. That means that in case we want to overflow a given buffer and hijack the execution flow, we have to make sure we first leak the canary itself. The NX bit is also enabled, which means that we cannot execute code from the stack or the heap. So there isn't a shellcoding possibility, for example. And we can say this executable isn't a position-independent executable. That means the addresses of the binary itself won't change between executions. They will remain the same. And last but not least, this binary has been compiled with partial RELRO. That stands for relocation read-only. This security mitigation, which we won't go into because that's not the purpose of the video, is what enables the attack we are about to see. With that being said, let us now execute the binary to see what it's actually doing. Your name, your register number, and we can say it simply prints some information. So this binary basically asks twice for input and then it prints irrelevant information. Let us try to break the program somehow, for example, providing a very long input. So the program didn't break. In fact, the binary finished its execution. We can see it read some bytes from the long input I just provided, and the remaining ones are here on the terminal. That means that we cannot hijack the execution flow. Let us try to execute it once again and to see maybe if there is a format string vulnerability. Let me provide my name and my register number. And as we can see, when it prints back the register number, here we have a format string vulnerability. The name apparently isn't of use. Let me check the first execution. Yes, as you can see in the first execution, the legit one, I provided Raz as the name and V as the register, and it printed back whatever I provided as input. In this case, however, since I am providing a format specifier, it is printing back a integer from memory, from a register, in order to be precise, as hexadecimal uppercase. So now let us disassemble this binary to better understand its inner workings and see how much space do we have here when this input is provided in order to craft our payload. In order to do so, I will launch Cutter as always. And here we have our main function. The first thing we see is, of course, there are canaries present on the stack, as we have previously checked with checksec. And so far we don't really care about them because we cannot hijack the execution flow, apparently. And we can see there are some prints, a printf, the first read call, which is the one that asks for our name, that reads up to 18 bytes and stores them into the buff buffer. Let us check where buff lives, and buff is RBP minus 90 in hexadecimal, so of course with just 18 bytes we cannot reach RBP or the saved return address of a main. After this read call, we have another printf that prints the register number string because it is about to ask us for the register number. And here is another call to read, which in this case reads up to 64 in hexadecimal or 100 bytes and stores them in the format buffer. Let us check where format is, and we can see it is at RBP minus 70. So once again, with just 64 in hexadecimal or 100 in decimal, we cannot reach RBP or the saved return address of main. So that's why we can't hijack the execution flow of this binary. simply because the reads call that we have do not read enough bytes. And then after this second read, we have a call to puts that simply prints the student profile string, and then we have a printf, which in this case, it does take a format string. As you can see, it is printing the contents of buff, which are passed via RSI register, which is the second argument to the function, and in the RDI register, it is receiving the format string itself. If we take a look at that memory address, we can notice that the address that the printf function is receiving as the first parameter corresponds to the string name, some tabs, and then the format specifier s. That is, the contents of buff are being interpreted as a string. However, in the case of the second printf call, let me check it, we can see that it prints without any format specifier per se. The contents of the format buffer that we have previously written into with the second read call are being printed as they are. As you can see, the address of the format buffer is being passed with the RDI register, which is the first parameter that the printf function receives. And here we have a format string vulnerability. As we have previously seen, we can write up to 100 bytes, which is more than enough room for us to craft the payload that we consider in order to abuse this format string vulnerability. Right after the format string vulnerability, we can see there are more printfs and puts, which we don't really care about. Then we have the check of the canary, and if the program doesn't fail with this function, that is, if the canary hasn't been modified or overwritten, the program simply exits. So now we have to answer the question, we have to think about, okay, we have detected there is a format string vulnerability, and what can we do with it? How we can abuse this binary in order to spawn a shell on the remote machine, on the victim's machine? Well, in order to answer that question, we have to consider several things. First, we have to take a look at what functions do we have in this binary. As we can see, there is a function called holidays. Let us take a look at what this function does. The holidays function also loads the canary, then it declares some variable and puts a value into it, which we don't really care, calls a printf, printing a given string, and then we can see there is a call to system receiving as the first parameter the bin.sh command. So this is the function that we want to execute, where we want to hijack the execution flow of the program. So we have a sort of red to win attack. Only in this case, we are abusing a format string vulnerability. So how can we reach the execution or provoke the execution of this function by the means of a format string vulnerability? So far, we know that we have a format string vulnerability with enough room to craft our payload, and we somehow have to hijack the execution flow of the binary to execute this function, holidays. We also know that the address of this function will not change between executions because this isn't a position independent executable, and we also know that we cannot hijack the execution flow by the means of a buffer overflow and overwriting the return address of main. So we have to somehow use the format string vulnerability to perform this execution flow hijacking. So in order for us to achieve such an objective, we have to think about the format specifiers that the printf family of functions work with. And there is a format specifier, which is n, that allows us to write the number of bytes printed so far into memory. This format specifier, whose mere existence is an absolute intrigue, is a mystery, at least for me, allows us to write into memory whatever we want and wherever we want, as long as the memory we are writing into is of course writable. It allows us to overwrite memory using a function that was initially thought to print data, which is curious to say the least. This format specifier takes the parameter as a reference, as an address, which will be pointed to by the internal printf function, and it writes into that very address the number of bytes we have printed so far. Do not worry if right now you don't fully understand the n format specifier and if you do not realize how we could actually abuse it. We will dig deeper into this very soon. For now, let us go back to our binary, because now we know that by the means of abusing a format string vulnerability, we can write whatever we want, wherever we want, as long as, of course, we have writable permissions wherever we are intending or pretending to write. So now the question is, what do we want to write? Well, of course, we want to write the address of the holidays function because this is what we want to execute somewhere. But where? Well, we can overwrite an entry from the GOT. But before stepping into it, in case you don't know what the GOT, Global Offset Table, is, or the PLT, the Procedure Linkage Table, or you don't know what do they do or what they are used for, let me recommend you a video I have recently uploaded on that very topic. In this video, called Global Offset Table, GOT, and Procedure Linkage Table, PLT, from the Binary Exploitation PWN101 series, we go into what these two sections, binary sections, are and how we can abuse them from a binary exploitation perspective. We explain what they are used for, how they work together in order to make the binary execution possible, and also how we can abuse them in order to perform several attacks like return to PLT or GOT overwrites, which is what we are about to do right now. You will find the link to this video in the description. Now, regarding the attack we are about to do, we have to bear in mind several considerations before beginning. First, this attack we are about to perform, which is called a GOT overwrite, because we are going to overwrite an entry from the global offset table, is actually possible because the binary has been compiled with partial relocation read-only. If the binary is compiled with full relocation read-only, this attack we are about to see isn't possible. If, on the contrary, the binary is compiled with no relocation read-only at all, it is vulnerable to this and other GOT attacks. However, it is very uncommon nowadays to see a binary with no relocation read-only at all, since partial RELRO is the default behavior for GCC, which is arguably the most used compiler nowadays. So you will almost always find or face binaries that are either partial or full relocation read-only. Also notice how the GOT section that we are about to overwrite, the GOT.plt specifically, is both readable and writable. It has write and read permissions, which is pretty important because we are going to overwrite into this section. We are going to write into it. And now the next consideration we have to think about is what GOT entry, what global offset table entry we want to actually overwrite with the address of the holidays function. Well, we have to overwrite a function that will be called, of course, after the actual vulnerability, after the actual overwrite takes place. In our case, the vulnerability happens with this printf function we have right here. And we can see that after the vulnerable printf call, there are calls to printf, to puts, and to basically nothing else. So we could overwrite either printf and put entries, right? Well, of course not. We have to take a look at what functions are being used in the holidays function, which is the function that we will execute after hijacking the execution flow. If we take a closer look, we can see that inside the holidays function there is a printf call. So if we overwrite the global offset table of the printf function with the holidays address, whenever we execute the holidays address, this printf call will call to holidays instead. So we will end up executing an endless loop, an infinite loop. And that's something that we do not want, because we want to execute this system call right here with the binsh parameter. So this situation leaves us with nothing else than just a single option, and that is overwriting the puts entry for the global offset table. And after all this theory, now that we know how we can abuse this binary, let us get into it and understand how we can abuse the n format specifier. The first thing when we have a format string vulnerability, as always, is of course finding out at what position from the printf perspective, that is, given its internal pointer, our input is. In order to find out, as always, I am going to use an easy to recognize sequence of bytes and then print several format specifiers. Since I'm using several format specifier, each one of these will advance the printf internal pointer by one memory cell until we hopefully reach our input. Let us execute it and see what we have here. As we can see, we can easily identify at a first glance that here is our input: 41, 42, 43, 44. 41, 42, 43, 44. These are the ASCII values, hex values of ABCD uppercase. So now let us count what position this is. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Our input lives at the 10th position from the printf's perspective, from its internal pointer. So let us write it down. And why do we care about the position of our input? Well, if you remember, we said that the n format specifier takes an address, takes a reference. That is, the n format specifier expects an address to the reference. If we know the position of our input, we could write an address right at that position and point the n format specifier to it. For example, let's say that our payload is, as we have seen, we want to overwrite the global offset table for the puts function. So let's say that I want to place at the beginning of my input that very address, and then by the means of using the n format specifier, I will write into it. How can I make the n format specifier point to that address so it dereferences it and writes right there? Well, by using the positional argument, which is this one, just like so. This simple payload we have right here, when we are asked about the register number, it will first send the address of the global offset table entry for puts, packed for 64 bits, and then we'll execute the n format specifier pointing it to the 10th position of our input, which will be this one right here, because we know our input is at the 10th position and each memory cell is 8 bytes. That's why we are packing for 64 bits, also because the binary is compiled for 64 bits, of course. Now we have also said that the n format specifier will write into the memory it points to the number of bytes we have printed so far. In other words, in order for us to know how many bytes we have to provide the n format specifier in order to write the value we desire into memory, we can follow this simple formula. The number of bytes we want to write with the n format specifier equals to the desired value, subtracting from it the number of bytes we have written so far. Let's say, for example, that I want to write the value 40 in a given address. So my desired value is 40 minus the bytes written so far, which correspond to whatever got printed by the printf function prior to the n format specifier. In this case, in this particular example, it is just this address. So it is 8 bytes, and the number of bytes I want to write is 32. That's the result of the subtraction. So using this format specifier, if I want to write 40 in decimal, just an example, we don't really care, in the address we have right here, I would have to print 32 more bytes. And how could I do so? How can I achieve it? Well, of course, using another format specifier. In this case, for example, using the X format specifier that prints integers as hexadecimal. Of course, we know so far that X by default prints a 32-bit long integer, which is 4 bytes, and we want in fact 32 more. So how can we do it? Well, we can achieve this behavior by padding the X format specifier with the number we wanted to print, which is 32. This format specifier right here is indicating the printf function that it must print whatever value the internal pointer is pointing to at this moment, which we don't really care, as a integer, 32-bit integer, uppercase hexadecimal, and pad it to the left up to 32 bytes. Since here we are printing 8 bytes and here we are printing 32 more, so far we have printed 40 bytes. And when the n format specifier gets executed, it will write into this address 40. Now, of course, the next logical step would be to actually try this and see if it works according to what we have just seen. But let me tell you beforehand, this won't work. This isn't an actual working payload for our exploit. Why? Well, please bear in mind that we are dealing with format string vulnerability. The function we are exploiting is printf. And printf takes a format string as a first parameter. Let us think for a moment about the result of this operation. We are converting the address of the puts entry from the global offset table into 64 bits and we are swapping its endianness. We are basically packing it for 64 bits. What is the result of this operation? Well, let us take a look at the actual address that we are dealing with here. In order to do so, we can, for example, go to main, go to the PLT reference for the puts, and then jump to the GOT entry. Okay, so now we can see that the address is this one we have right here. The result of converting this address into a 64-bit useful integer using the pack function from pwn is the following one. Remember that we are working with a little endian architecture, and that means that the least significant byte is written first, that is at a lower address. And this leaves us with the following result. We have, just like so, the bytes of the address, which are this one we see right here, in little endian of course, and then we pad them with zeros whenever it's needed, so we end up with an integer that is 8 bytes long. It doesn't fit on the screen, but you understand that we are padding with zeros to the right until we reach 8 bytes. So this address we have right here is the 8 bytes little endian equivalent of the address of the global offset entry for puts. Now, since we are working with printf that expects a string as a format string, whenever it encounters a null byte, it considers that the format string itself ends. It will stop reading. So whatever we have following this byte gets ignored, because remember that when we are working with strings by default, in the vast majority of languages and architectures and CPUs, strings are null terminated. That is, whenever there is a null byte, it indicates that the string has finished. So printf will consider only these 3 bytes we have right here. Now, going back to our exploit, we of course don't want printf to stop reading right in the middle of this address. We want it to read our actual format specifiers and then reference the address. In order to do so, what we have to do is swap the order of the operators of our payload. This way, whenever the format string vulnerability, the printf function, encounters a given format specifier, it will execute it, and we can reference further on the stack, further positions, for example, position number 12, and then the format vulnerability will keep reading until it faces the null bytes and it will finish. But we don't care because we already executed our format specifiers. Now, of course, please keep in mind that this changes our payload. So now we want to write 40 bytes, of course, but how many bytes have we printed so far? We have printed none. So 40 minus 0 is actually 40, so we are going to write here a hexadecimal integer with up to 40 bytes of padding, and we have to reference the actual position of the stack where our address is in order for the n format specifier to reference it, to be able to dereference it. And here we have to be very careful because there is another little trick. Bear in mind that we are working in a 64-bit binary, so each memory cell comprises 8 bytes. When we are writing our input, each character is 1 byte. And how many bytes do we have here? We have 9 bytes. We have 9 characters. That means that these first 8 bytes will be placed into position number 10 from the printf function, from the format string vulnerability perspective. And then this n character we have right here will be placed into the 11th position. And we have to fulfill this 11th position. We have to pad it with random values until we place the address we want into the 12th position. So we managed to actually reference it, because we cannot reference positions at their half. We cannot say, for example, the address is at position 11th and a half. Since this n is in the 11th position, we have to write 7 more bytes until we fulfill a full memory cell, and then this address will be, of course, in the 12th position. That way, when this format specifier is executed, it will indeed reference the address at the 12th position, which is this one right here, and we'll write into it the bytes we have printed so far, which are 40 in this case. So now let us test it to see if we are actually writing a 40 value into the address we are providing here as a parameter, that is the global offset table entry for the puts function. In order to test it, what I usually do is writing the payloads I have into a given file and then test it using radar2. In this case, the junk payload is 12 in hexadecimal because the first read function is the number of bytes it will actually read. Since read won't stop reading when it encounters, for example, a new line character or a null byte, it will read from the file until it exhausts the full 18 bytes. So I am simply providing garbage. That is 18 bytes of garbage and then the actual payload. Now we have to execute our exploit in order to generate the payload file. Here we have it. And now in order to test it with radar2, I will use the uppercase R flag that allows me to specify what I want as a standard input. In this case, it is the payload file. And then I am once again specifying the actual binary I want to debug. Now, after launching Radare, I am placing breakpoints right where the vulnerability happens and right after it, so I can inspect the results of the vulnerability itself. I am now executing the binary. It has hit the first breakpoint, and let us now print the section.got.plt, which is where the values are. In this case, we can see the global offset entry for the puts function has been already resolved, points to its actual value in glibc. And now, if our payload is correct, we are executing once again. We have hit the breakpoint where the vulnerability took place already, and let us inspect once again the global offset table. As we can see, the puts entry for the global offset table has been overwritten, only that the value we have here isn't the one that we expected. Well, we have to of course bear in mind that 28 in hexadecimal is 40 in decimal, and that is the number that we wanted to write. However, we expected to overwrite the full address, the full 8 bytes value of this address, and apparently we overwrote only the first 4 bytes, as you can see here, 1, 2, 3, and 4. Please notice that the prefix 7F40 was already present in its legit value, 4F40. And why is that? Well, it is because the n format specifier also writes an integer which is 4 bytes by default. That means that it will overwrite only 4 bytes. So how can we manage to overwrite the full value of this global offset entry for the puts function? Well, we know that at this point is where the value starts, which is address 404018, but nothing is preventing us from writing, for example, 2 bytes higher. So we can overwrite, for example, starting from this position right here. Here we will write 4 bytes, and then we will overwrite with whatever we are interested, 2 bytes lower. Let us write the exploit so you can better understand what I mean here. But first, now that we are reaching our final payload and we are finally understanding how to abuse the n format specifier, let us take a look and see what is the address of the holidays function. We can see it is 40123b. So we have to overwrite the global offset entry of the puts function with this very address. We could of course try and write all this address at once by providing the enough padding to the X format specifier, but please bear in mind that whenever we are sending an actual payload to the server over the network, it will respond back to us with the whatever value it printed. We don't want to saturate the network. In fact, this number we have right here equals to almost 4.2 million bytes. That is for almost 4.2 megabytes. And we don't want to receive 4.2 megabytes of data. So instead, in order to actually make use of this technique, what we can do is writing at the address of the puts entry in the GOT +2, we will write this 40 right here. And then at the address of the entry, we will write this payload123b. And now of course you may think, well, if we are writing first the address plus 2, when we will write this 123b, won't it overwrite with zeros whatever we have on the upper addresses? Well, I got you covered. Don't worry, because remember that in the printf function we have also what is known as length sub-specifier. Just the same as we are able to specify the L length sub-specifier in order to print 8 bytes instead of 4, we are able to specify the H, that stands for half, in this case short int, which will write only 2 bytes instead of 4. So in the second overwrite, we will overwrite the memory we point to with the N format specifier with only 2 bytes, not 4. So this is our final payload. It is almost finished. Let us understand what we are doing here. First, we have said that we will overwrite the global offset entry for the puts function, starting from its address plus 2, that is that we will overwrite from this byte on up to 4 bytes, and we will write 40 in hexadecimal. Please bear in mind that this value we see right now doesn't correspond to its actual value when the dynamic linker resolves. So we will overwrite with 40, and then at the address of the puts entry, that is starting from the very first byte, we will write the remaining bytes with the needed values in order to achieve the address of the holidays function. So the math is very simple. First, we want to achieve a 40, which is 64 in decimal. Please bear in mind that we are working with decimal values whenever we specify the padding for the printf function. So we want to write 64, and we have printed so far none. So we expect a 64. Here we have it. And then we want to end up with 123b in hexadecimal minus the number of bytes we have written so far, we have printed so far, and that is 64. And that's what we have specified here. And please bear in mind that first we are writing at the address of puts plus 2 in the GOT, and then at the address of puts in the GOT. And in this second read, we are writing only 2 bytes, not 4. That's why we are using the H length sub-specifier here, in order to indicate to the printf function that this N operator will write at half, will write a short int, not a full integer. Now there is only one thing remaining for us, and that is the positional argument that the N format specifier will reference. In order to solve this, we have to just count the number of memory cells we are fulfilling, we are completing with each byte we are writing. Remember that each memory cell is 8 bytes, so we count 8. We have our first memory cell, that is position number 10. We have 1, and then 7 more. That is our second memory cell, that is the 11th position. And then we have here 5 more bytes. So in order to fulfill it, we have to provide 3 garbage bytes as padding, and this becomes another 8 bytes, fulfilling the memory cell corresponding to the 12th position. So this will be our 13th position, and this is the 14th position. In other words, the first N format specifier will reference to the address written in the 13th position, so it will write into it, it will dereference and write there. And then the second N format specifier, which will write in half, will write in the memory address contained in the 14th position, which is this one right here. It will dereference it and will write into it. Now, I won't test this payload because we are sure about what we are doing, we understand the theory, but you know now how you can debug your payloads by using a file. So what I will do now is, of course, invoke my process and simply test if it actually works. Notice how this time I'm not even printing the output because I do not really care. So we are just providing the junk payload and then the payload for the format string vulnerability, and we simply want to spawn a shell. Let us try it. Notice how after executing the payload we are printing in the register white spaces because this is the padding we provided the format specifier with, and now we should be able to execute a shell locally. Okay, it works. Let us test it remotely. Remember, we have to exploit this binary in the victim's machine on the remote server. Okay, I have already deployed the TryHackMe's machine, remote machine, and I have changed my process. Instead of a local process, I want my exploit to connect to a remote machine. The binary will be running in a given IP and a given port. Let us test it. Here is a small gift for you, and as we can see, it runs with no problems. So we have successfully exploited the global offset table GOT overwrite. Let us first grab the flag and see if it actually works. And it is correct. In this video, we have seen how to overwrite memory with arbitrary values by the means of abusing a format string vulnerability. Using the n format specifier, we are able to write the value we want at the address we want, as long as the memory is writable. And we performed an attack that is referred to as global offset table overwrite. An attack that, remember, is only possible because the binary was compiled with partial RELRO, relocation read-only. By performing a GOT overwrite, we are able to hijack the execution flow and forcing the binary to execute a function of our choice instead of the intended function. In this case, we overwrote the entry of the GOT for the puts function, so whenever puts is called, it executed our function instead of the intended puts function from glibc. I hope you liked the video and found it useful. If there is anything you want to say, leave a comment below. And remember, exploit code, not people. See you in the next one. Until then, GG.